Okay. All right, guys. So we're going to be learning quite a bit of stuff today. Is it going?
Put up low battery.
Oh, it's low battery? Okay. Well, hopefully it gets through this. We're going to be talking about quite a bit of stuff. Okay, so we've been factoring. I've talked about how factoring is essential for this unit. It's going to get where you really need it now, okay? We're going to start talking about graphing. We're not going to be graphing, but we're going to be talking about how you identify vertical asymptotes, horizontal asymptotes, removable discontinuities, finding where domain restrictions are. Eventually, we're going to get to, and we're just going to be filling this out, x-intercepts and y-intercepts, but the focus today is going to be on these four right here and how they're all pretty much, well, these three are interconnected: vertical asymptote, removable discontinuity, and domain, very much. And that's where we're going to start, and we're going to end with horizontal asymptotes. Hopefully you guys feel pretty confident when we end about what we're doing, because you already know all the mechanics to do it. Now just identifying it is very simple. Okay, so vertical asymptotes. Where you get vertical asymptotes has everything to do with not being able to divide by 0. So for example, and that's the same with domain restriction. So let's start with domain restriction. And just so you guys know, always start with domain restriction, because here's the deal. Every domain restriction is going to either be a removable discontinuity or it's going to be a vertical asymptote. Every single one, okay? So what does that mean? Well, let's get started and we'll figure it out. I'll show you. So what can x not be if you cannot divide by 0? X can't be what? -5. Okay, so here's my domain restriction. What does that mean? It means that x can be anything except -5. It can be anything except -5. That domain restriction is either going to be a removable discontinuity, okay, or it's going to be a vertical asymptote. And this is how you can tell. Look at your function. If it cancels with something up top after it's been factored, then it's a removable discontinuity. If it doesn't cancel, then it's a vertical asymptote. Okay, you guys got it? So, does it cancel with anything up top? No. All right, so what this is saying is the function cannot be -5. So at -5, something's got to be going on. Okay? Removable discontinuity is going on, or vertical asymptote. Because it doesn't cancel, at -5, there's a vertical asymptote. Does that make sense? So look, you might say, well, this says x can't be -5. So for the function, x cannot be -5. So something is going on at -5. A vertical asymptote is happening at -5. Does that make sense? So in the function, x can actually be -5. So you have a vertical asymptote at -5. Okay, that's why you have the can't equal this, and then it can all of a sudden right here. All right, so let's look at the next one. All right, on this one, we're going to factor the top part out, and that's going to be the difference of squares, so x minus 2, x plus 2. All right, let's talk about the domain restriction. Start here. X cannot be what? It can't be positive 2, because 2 minus 2 would be 0, and you'd end up dividing by 0. So it can't be 2. So at 2, either a vertical asymptote's happening or a removable discontinuity. Does this factor on the bottom cancel with something up top? Yes. Yeah. Okay, so it cancels right here. So that means at 2, it's not a vertical asymptote. It's a removable discontinuity because it canceled. Do y'all understand that? So as far as vertical asymptotes are concerned, you don't have any. None. No vertical asymptotes. Because it canceled. Because it canceled, it's actually a removable discontinuity. And I'm going to explain the difference between the two in just a second. So let's go ahead and do one more. So in order to be able to cite what the domain restrictions are on this, got to factor it. And again, guys, you have to be able to factor. If you cannot factor by now, you need to go back and watch one of the videos and learn, okay? We just had a test over it, so you need to know it, especially just the basics. Know sum of cubes, difference of squares, right? Know basic trinomials, and know how to take the GCF out consistently. That's what you need to know, all right? So here's the bottom factored out. So my domain restrictions, x can't equal this, x can't equal that. So what are they? X can't equal 3, and that's a positive 2, so x can't equal -2. Okay? Everybody good there? Those are my domain restrictions. So again, I'll say this one more time, so listen carefully. Every single domain restriction is either a removable discontinuity or it's a vertical asymptote. It's not both, it's one or the other. So because I have two, that means I have either two vertical asymptotes, maybe I have two removable discontinuities, maybe I have one of each, right? And it all depends on what cancels and what does not. Y'all understand that? Okay, so does anything cancel? No, so they're both vertical asymptotes. So I have a vertical asymptote at x equals 3, and I have a vertical asymptote at x equals negative 2. So far, so good? Let's see what this looks like now. I'm going to go ahead and graph it. So I was working with the other class on some concepts. So I'll erase that. Let's go to a standard zoom. Tab. Okay, notice when I actually put it in, I use that second divide, so I get an actual fraction there. It makes it a lot easier to actually type in. Can somebody tell me what that equation was? 5x divided by x squared minus x minus 6. Okay. And remember, we factored this to be x minus 3 and x plus 3. So where are my two vertical asymptotes going to be? 3 and negative. 3 and negative 2. All right, so here it is. All right, let's zoom out a little bit so we can get a better view of it. Get that out of the way. Okay, 3 and negative 2. So let me see if I can do it this way. So you can, right there. You can kind of see it right there. Positive 3, negative 2. You see both vertical asymptotes, right? Okay, so both vertical asymptotes are there as we predicted. What would it look like if one of them was actually a removable discontinuity? So which one of these vertical asymptotes, let's just start messing around with this, because what I want to explain and show you is what a removable discontinuity actually is. I've described it before as an infinitely small hole in the graph, right? Something that causes it to be discontinuous. For example, as I draw it, I kind of go, and then I have to pause, pick up my pen, put it down, and keep going. So it's defined as being discontinuous. Let's see. Okay, so which one of those vertical asymptotes do you want to get rid of? Let's get rid of the negative 2. Okay, if I'm going to get rid of the negative 2, that means the x plus 2 factor has to cancel, right? And that would cause it to be a removable discontinuity. So let's just make it up now. So I need to put times, what do I need to put up here? Would that cancel with the x plus 2? Exactly. Okay, that would cause it to cancel, right? And if it cancels, watch what happens with this vertical asymptote. Okay, so that's gone now, right? We still, I need to zoom out a little bit to see it, but we still have this vertical asymptote at positive 3. But the one at negative 2 is gone, right? But that doesn't change the fact that it's still a domain restriction. So remember, we just kind of made this up. We just put an x plus 2 up here and assumed that it canceled. But there's still a domain restriction, right? So the graph still does not exist at negative 2, right? There's this infinitely small hole because it canceled. Infinitely small hole called a removable discontinuity, okay? So it's a removable discontinuity. So this is what it would look like. Control T. So at 3, you see the vertical asymptote. It says undefined. And at negative 2, it's still undefined. You just don't see the vertical asymptote, okay? So in a way, visually speaking, we have removed that discontinuous point, right? So you guys need to remember that word. And people struggle with it, but it makes a lot of sense, all right? So removable because you're canceling it out. Discontinuity, discontinuous, all right? You got it? So go ahead and try it. Removable discontinuity, say it. Removable discontinuity, all right? Sometimes you just feel so dumb saying that, like, but then at the same time, when you get it down, you sound really smart. It makes somebody like me sound smart. That's why you guys think I'm smart.
Say it like a narrator voice.
Huh?
Say it like a narrator voice.
Give me an example.
Removable discontinuity.
Wait. Go. You got it.
Removable discontinuity.
Okay. All right. You got it. You're too good at that. I'll pass. I'll pass. All right. Let's keep messing around with this. Let's just get the idea. So we still have the vertical asymptote at positive 3. If I was going to get rid of that, then my equation would have canceled out on that one as well. So I would have had also a times x minus 3 up top, right? And now I'm not going to have any vertical asymptotes. Does that make sense? Because both of them would have canceled in that case. Yeah? So no vertical asymptotes. It looks like a vertical line. It pretty much is a vertical line, but you still have two discontinuous points. All right? And they're both still at where we already know they are, at positive 3 and negative 2, infinitely small points, okay, called removable discontinuities. Does that make sense, guys? Y'all understanding it a little bit? So what I'm teaching you right now, if you go back over here and you look at this, our objective is to get the first four. We should understand now domain, right? And every domain will express itself as a vertical asymptote or a removable discontinuity. Does that make sense? Okay, so let's go ahead and practice just those first, and then we'll end the class with horizontal asymptotes. Horizontal asymptotes, that's a really cool concept. Okay, so start off with domain restrictions. So you look over here, and we find out, because it's already factored for us, that x can't equal two things. What can it not equal? Positive 1, positive 3. Positive 1, positive 3. So each one of these domain restrictions will express itself, right? It will visually show up on the graph as either a removable discontinuity or a vertical asymptote, right? So which is which? Does anything cancel? Nothing cancels up top, so you actually don't have any removable discontinuities. If something did cancel, you would have a removable discontinuity, right? So both of them, because they don't cancel, are locations of vertical asymptotes. You got it? Okay, let's look at the next one. Start off with a domain restriction. So we simply have an x on the bottom. So if we can't divide by 0, then what can x not be? 0. Simply 0. Okay, x cannot be 0. Does that cancel with anything up top? No. So again, you don't have any removable discontinuities. You have one, which is that, vertical asymptote at x equals 0. Okay, let's find some removable discontinuities. So, number 6. That's a good example. All right, let's start off with domain restrictions. Always start with this. There's 3 things that x can't be. X cannot be negative 3 because of this, positive 3 because of that, right? 0 because of this. So x can't be 3, negative 3, or 0. Now, again, let me reiterate this. Every single one of those domain restrictions is either a removable discontinuity or a vertical asymptote. You guys are getting the point now? One or the other. So you're going to have 3 total. So which are which? Okay.
Why can't it be 0?
Because if x were 0 right here, you would take 0. And even though that's a 0 and that's a 0, what's 0 times 3 times negative 3? 0. So you'd be dividing by 0. So the question was, why could it not be 0? All right. So you're going to have 3 total of these things. Now what cancels? Minus 3 and minus 3. Okay, so that means x, this one was giving me the domain restriction of x couldn't equal 3, because 3 minus 3 would be 0. So when x is 3, you're actually going to get a removable discontinuity. Okay, because that's the one that canceled. So when x is 3, removable discontinuity, because it canceled. Do the other 2 cancel? No, so those are vertical asymptotes. So notice I have 3 total. Each one of my domain restrictions express itself as either a removable discontinuity, because it cancels, or vertical asymptote, because it doesn't cancel. You guys following?
Yeah.
All right, good. All right. I'm considering continuing on in this video, chopping it off, or should I just jump to explain horizontal asymptotes? I think I'm going to do that so the video can kind of be fluent. All right? So do y'all understand? Here, on your own, 30 seconds, so it's going to be a 30-second break in the video. Why don't you try to do a few more of those? And we'll have a music break. What song do you want me to sing?
No, Dance in the Square for 30 seconds.
Huh?
Dance in the Square for 30 seconds.
Nah. All right, make sure you get this. No, I need to write that down again. Sorry, I threw away the paper. Okay, I'm gonna do one more really quick. So because of this one, x cannot equal three things. X can't equal 4, -3, -1. 4, -3, -1. Nothing cancels with what's up top, so there are no removable discontinuities. Every single one of them is a vertical asymptote. Is everybody okay on that? Okay, great. Now this is a really neat concept that I'm about to explain, and it's semi-deep, okay? I'll try my best to explain it. What?
Sir, what about 5?
Number 5. Oh, that is a good question. Okay, let's do number 5 real quick. Perfect. All right, so number 5, you get vertical asymptotes or domain restrictions because at that spot you can't divide by 0, right? That's the idea. You can't divide by 0. So I'm going to try to explain the best I can thinking in numbers. Literally, this is actual algebra right here, thinking out loud in numbers. I can't divide by 0, right? That means 2x minus 3 can never equal 0. Does that make sense? Because if it did, then I'd be dividing by 0. I'm literally thinking in numbers right now, okay? 2x minus 3 cannot equal 0. And if 2x minus 3 can't equal 0, then 2x can't equal 3. Because if it did, you'd have 3 minus 3, right? So 2x cannot equal 3. Notice I'm just solving this algebraically, right? 2x cannot equal 3. And if 2x cannot equal 3, then x cannot equal what? 3/2. So the point is, if x equals 3/2, you're going to end up dividing by 0. So what's your domain restriction?
0.
X cannot equal 3/2. Does it cancel with anything up top? No, so you don't have any removable discontinuities. Okay, so because it doesn't, you have a vertical asymptote at x equals 3/2. Okay? So it's pretty neat. Honestly, guys, the better you get, the more logical things are, right? And I like that example just because it literally shows words, thinking, logic, and numbers, right? That's what that was. Okay, so now let's talk about horizontal asymptotes. This is a really, really neat concept, but kind of difficult to explain. So what a horizontal asymptote is, it's talking about end behavior. Okay, what is an end behavior? End behavior means as I go to infinity on my function, right? As I get bigger and bigger and bigger and bigger and bigger, what does the end of the function look like? How does it behave toward the end, right? End behavior. What does it look like? Does it settle on a number? Does it keep just expanding exponentially toward infinity? Is it stopping? Okay. As I go toward negative infinity, what does it look like, right? So as I go to infinity and negative infinity, does the function look like? That's the concept of end behavior. As the x's get infinitely big or infinitely small. Does that make sense? As it keeps going. So I'm going to show you a quick way to remember it, first of all. All right, so I'm just going to not give you the logical part. I'm going to show you something that's going to help you remember it, something that's going to help you pass the test. Then I'm going to explain why it works that way. The explanation is the difficult part, okay? Here we go. So as far as how to pass the test, you can have 3 situations, and it's all based on the degree of the function or the degree of the expression. So up top, what degree is that? First degree, right? It's x to the first power. What degree is on the bottom? First degree. So you have a first degree over a first degree, right? So if you have the same degree over the same degree, that's one situation that happens, where it's both the same degree on the top and the bottom, right? Second situation that could happen is if you have a bigger degree on top, and in this case, what degree is that? Second degree. So if it's bigger on top and smaller on bottom, right? So you have a higher degree on top and a lower degree on the bottom. Y'all follow that? Okay, third situation, you can have a lower degree on top and a higher degree on bottom. There's only 3 cases that can happen. Does that make sense? You can have a lower on top.
Why are you telling us high, sir?
So I'll explain. Because I told you to memorize for the test, right? Just to understand the test. If you ever have a higher degree function over a lower degree function, high over low rhymes with no. Okay? So as far as horizontal asymptotes are concerned, you don't have any. You have no horizontal asymptotes.
High over low what?
Rhymes with no.
Low over high, right with.
Why?
Oh.
Okay? So
Low key. So
if it's a lower degree function over a higher degree function, low over high, it rhymes with y. So it's y equals 0, okay? So high over low, you don't have a horizontal asymptote. No horizontal asymptote. Low over high, y equals 0, okay? If it's the same, then you grab from the coefficients. So the coefficient of the first degree x is 6, and the coefficient of this first degree x is what?
1.
1. So it's y equals 6 over 1. And you just write the coefficients like that. Now let me explain. That's it. That's how you identify horizontal asymptotes. Let me explain why. And this is the very valuable, logical, but difficult to explain part. Okay? It has a lot to do with, this concept you're going to learn in calculus with things called like limits, okay? As x approaches a certain number. And in this case, it's as x approaches infinity, and as x approaches negative infinity, what happens to the function? Okay, so the reason that the same over same works the way it does is because if I have, let's just use this example. If I have a really big number, a huge number, 5 is not going to make a difference at all. So the reason you don't deal with the 5, all that matters is the coefficients, is because 5 ceases to matter, right? When you're dealing with small numbers, it might matter. So for example, like if x is 1, that's a pretty small number. So what's 6 times 1?
6.
6 over 1 plus 5? What's 1?
6.
Yeah, 6 equals 1, okay? That's when x is a small number. What if it's a little bit bigger, just a little bit bigger? So like what if x is 10?
60.
6 times 10 is 60. 10 plus 5 is 15. So that's 4. But you see now, the top is starting to take off, right? But we're not at big numbers yet. What if x is 100? You have 600 over 105. Does the 5 even really matter that much anymore? What's it getting close to?
Nothing.
6 over 1. It's getting close to 6, isn't it?
No, it's like 40 over 7. Right.
It's getting close to 6, right?
Yes.
What happens when x is, now I'm saying as x goes to infinity, what happens? So let's take a huge number. What if x is 1,000,000? 6 million over 6,000,005? Does the 5 make a difference? No. So as x goes to infinity, it's landing on 6. Does that make sense? So what does that look like? Let's type it in here. Okay. Okay, so tab, we had 6x divided by, oops, that stinks. Okay, we had 6x divided by x plus 5. First degree, first degree. We said it would settle on 6, right, the horizontal asymptotes? So as it goes to infinity, you see how it's starting to settle on 6? So let's zoom out even further. Well, let's just change the window. Everybody understands what we're looking at right now, right? What I'm about to do is change the window huge. I'm going to see from, let's say, 1 million to negative 1 million, and then I'm going to also view it between maybe 5 and negative 5 and 10. Okay, here we go. So menu, window, window settings. I'm going to change what I'm looking at from negative 1 million all the way to positive 1 million. Keep in mind, you're not going to see anything in the middle because we're zoomed so far out that way, right? And y minimum, let's say negative 5 up to positive 10. We said it's going to settle on 6, right? So what this is going to look like is a solid line going all the way across at 6.
Whoa.
Okay? Does that make sense though? So we're zoomed way the heck out. I think I put negative 10 million accidentally. Okay, but we're zoomed way, way out. And it's right on 6. Does that make sense? So as it goes to positive and negative infinity, the end behavior is it settles on 6. So that's why that makes sense. Okay, so that's why you take the coefficients. So if it's a higher degree function over a lower degree function, guys, when I start getting big numbers like 100, do you think that -4 and that -2 are going to matter at all? No, all that matters is the biggest degree. So for example, let's talk about 100. What's 100 squared? Anybody have it quick?
1,000.
I think it's 10,000. So 10,000 minus 4, that's pretty much 10,000 still, right? Divided by 100 minus 2. It's pretty much 100. 10,000 divided by 100, so it's 100, right? What if we get bigger? What if we talk about a million? Do you realize the difference between a million? I'm not even going to put the minus 4. It ceases to matter. A million squared over 1 million. A million squared is huge, right? So it's literally this. A million squared is, that's how big a million squared is, right? And that divided by that is a million. So you see, as the numbers are getting bigger, it just keeps going, right? There's no point where it plateaus. It doesn't stop on any number. That's why you have no horizontal asymptote. Does that make sense? Because the degree on the top is kind of taking authority. It's just taking over. As numbers get huge and they square with themselves, they're just getting massive. And there's no slowing it down, really. Does that make sense? Okay? Same as on the bottom. When the degree on the bottom is bigger, well, what's up top, all this stuff kind of ceases to matter. And this is just going to start taking authority as the numbers are getting huge, right? And they're multiplying by themselves again, they're being squared. You're pretty much going to have something that looks like this, 1 over some massive number, which is pretty much 0. So that's why this one ends up being y equals 0. This one ends up being undefined, or it just doesn't really have a horizontal asymptote, right? And this one is you just take the coefficients. Does that make sense, guys? That's why. Okay, so now you've done a lot of these as far as the domain, horizontal asymptote, vertical asymptote. Remember, these are all very much dependent on each other. Oh, I'm sorry. These are very much dependent on each other. Horizontal asymptote is what we just talked about. So it really is this easy. Is it a higher degree function on top or bottom? Or is it the same?
It's the same.
It's a low one.
Yeah, it's low on top, high on bottom. Low over high, right? So rhymes with y. So what is the horizontal asymptote?
0.
Y equals 0. Okay? Low, right, no degree, over first degree. Low over high, y equals 0. Same, right?
True.
Same over same, first degree, first degree. So what do I do?
Coefficient.
Lower the coefficients. 4 over what? So y equals 4 over 1, or you can just write that as 4. So x times x times x is eventually going to be x cubed on the bottom. X times x on top is x squared.
So it's low.
So it's low over high.
So y equals 0.
So pretty easy stuff, right? Does that make sense? That's it. Okay, let's see if there's anything else that needs to be explained. This is a good one. This needs to be explained. So I'm on the other side. If you look at this, I just want to talk about domain restrictions with something like that real quick. A domain restriction would happen when you can't divide by 0, right? Where you can't divide by 0. Does this make sense, guys? Domain restriction happens when you can't divide by 0. X squared plus 4. The question is, can you ever make x squared plus 4 equal 0? No. I mean, make x a negative number. What's like negative 2 times negative 2? Positive 4, right? Plus 4 is 8. Okay, maybe positive 2. Let's try positive. What's positive 2 times positive 2? 4. Plus 4 is 8. Maybe 0. What's 0 times 0? 0. Plus 4 is 4. There's no way to make it 0, right? So the point is, there's nothing to restrict your domain here. There are no domain restrictions. So you can say none as far as domain restrictions are concerned, or when there's no domain restrictions, what do we call that? Any idea? There's no limit to your domain. It's every single number. It's every single number.
All real numbers.
All real numbers. Your domain restriction is nothing. It can be any number, right? Which means if there's no restrictions, you're not going to have any removable discontinuities. You're not going to have any vertical asymptotes. You don't have any domain restrictions, right? So they're not expressing themselves in any way. Vertical asymptote, same over same. Or I'm sorry, horizontal asymptote, 2 over 1. Okay. Any questions, guys? Perfect. All right. Stop. Nope, didn't stop.